Hello everyone. So let's continue with the topic of conformers, right? In our last lecture we have studied about many things about chair conformer, axial equatorial positions, how to draw board conformation, twist board conformations. So let's continue with the topic. Draw conformers of first it is 1 3 5 trichloro cyclohexane. Okay, so if you are asked to draw 1 3 5 trichloro cyclohexane, let's see. One, two, three, 4, 5, 6. Okay, so if I'll start from this position as one position, so down, down, down. You can check it as 1, 2, 3, 4, 5, and 6. So this is 1, 3, 5 trichloro cyclohexane chair form. Now if we talk about the stability, we can see here that we have not been asked whether it is cis form or trans form. So I have to draw all the possibilities. So first of all, let's see this one. This is from one position downside, so it is equatorial, down, equatorial, equatorial. So all three chlorine atoms are in equatorial positions. So simply you can understand that this one will be most stable conformer. Okay, but let's see the two cis and trans forms of this one first. If all three chlorines on same side, either it is wedge or a dash form. So I am just drawing dash form of all three chlorine. Okay, so this is cis form. And now suppose any one chlorine in wedge and the other two are in dash, or if any one chlorine in dash and the other two are in wedge, then you can say it will be trans form. So if asked that draw the chair conformers of the geometrical isomers of this structure, so for this structure the geometrical isomers will be this one cis form and this one trans form. So let's see, if all three chlorine atoms on same side, here you can check it is down, it is also down, and this one also down. So you can see for this structure, for cis form, it is your cis form. Okay, now for cis this is perfect. Now let's draw for this trans form. So for trans form, what I have to do, if I'll see 1, 2, 3, 4, 5, so any of the two, because if I'll say this one in wedge or this one in wedge or this one in wedge, that all three are same. So any one in down, then the other two will be in upside. So from this I can observe that keeping 1 and 3 in down and taking 5, 1 upside, so it will be this trans form. So taking any one of these in upside, I can make the trans form, right? So simply if I'll say down, down, and this will be up, chlorine. So this is your trans form, because these two chlorine are in downside and this one in upside. This is equatorial, equatorial, and axial. Okay, so this is your trans form. Now there is one more possibility. If you will think, see, if I'll make two chlorine upside and one downside, suppose this one is upside, this one is upside, and this one downside. Now here also you can think that in this one This is your 1, 2, 3, 4, 5, 6. 1 is upside, 3 is upside, and 5 is downside. So it is also trans, right? With respect to this trans, both these are possibilities. So now the question arises, which will be more stable? So let's see axial and equatorial positions. Okay, if I will see this one, it is down equatorial, so it is axial. Upside, it is up, it is axial. This is your axial and this is your down equatorial. So among these two, which will be preferred? This structure will be preferred, right? Why this will be preferred? 2Cl in equatorial positions. The bulkier group, if occupies equatorial position, will be more stable, right? So for this question, this is cis form, this is trans form, this is your cis most stable form. Because one more case in this cis also, what you can do is, in this cis form, if all the three are upside, see, all three are downside and equatorial. So if all three are upside, so it will be axial. All three will be axial. So that will be the most stable form for 1,3,5 trichlorocyclohexane. Okay. So I think you have understood. Let's take another one of the most important example. N-methyl piperidine. N-methyl piperidine. Now first of all, let's see what this compound is. This is your N-methyl piperidine. Okay. So if I have to draw the conformer of this compound, how will it will be? It is again 6-membered ring. So better to draw chair form. This one as nitrogen. So you can see here that this nitrogen is having lone pair as well as methyl. So if I keep methyl this side in equatorial and lone pair in axial, or another case will be this one as nitrogen having methyl downward and lone pair in equatorial. So you can simply say this will be preferred because this is more stable. Now if I will simply say piperidine, it simply means this 6-membered ring, it is heterocyclic. See, if I will say about this compound, it is heterocyclic. First, second, Du or Dbe, double bond equivalent or degree of unsaturation for this compound will be 1 because it carries one ring. Okay, and as the ring comprises of carbon as well as nitrogen atom, so it is heterocyclic. This is N-methyl piperidine. If you are told to draw only piperidine, so that will be your nitrogen having a hydrogen atom simply. Okay. So this is N-methyl piperidine. Now let's take the example of cis alpha methyl piperidine and second trans alpha methyl piperidine. Okay, so students, as I told, piperidine means simply this structure, nitrogen having lone pair and one hydrogen atom. This is your piperidine. Okay, now alpha methyl means the alpha position with respect to this nitrogen will be this position. So this position will be your methyl, in this case cis, and this in this case trans. So let's draw one by one. If I have to draw cis form, this is your nitrogen. Okay, now this is having hydrogen and methyl, and this nitrogen is also having hydrogen and methyl. So if this nitrogen having hydrogen and this carbon also having nitrogen, so what will be the case? If I am telling cis form, it simply means both hydrogen must occupy same side, either upside or downside. Now let's see. If I will draw both hydrogen upside, so what will happen? Methyl will come in equatorial position, so that is the better case. So I will draw hydrogen this side, methyl this side, and here hydrogen this one. Okay, so in this case what's happened? Nitrogen hydrogen upside, here also carbon hydrogen upside. So with this respect it is cis form. Okay, so this is your cis alpha methyl piperidine stable form. Another possibility was if I draw nitrogen hydrogen downside and this hydrogen also downside, but what will happen in that case? Methyl will go upward in axial position, that will make it lesser instability. Okay, so this is your cis. Now if I have to draw trans alpha methyl piperidine, what I will do? This is your nitrogen. Now for trans, I'll make this hydrogen this side, methyl this side, but at the same time I'll make this lone pair this side and hydrogen this side. So you can see with respect to hydrogen we can say cis or trans. Hydrogen here upside and hydrogen here downside, so it is trans form. Trans. Now if you are asked that in between this cis and trans form which is more stable, so here you have to understand it is not about configuration now, it is not about cis or trans form, it is all about now conformation. You have to observe both the conformers and then understand which is having more stability due to lesser strain. Okay, so if I'll say in this structure, so methyl is in equatorial but lone pair in axial position. So just imagine the Newman projection formula, lone pair in axial and methyl in equatorial, and here you just assume Newman projection, this pair as well as methyl in equatorial position. So if you remember that case, this part, this side will be your another ring. Okay, so if you remember that part, so this nitrogen is having, if lone pair this side, then this methyl will be from second carbon this side, and both are gauge to each other. So this is the most stable form. So among cis alpha methyl piperidine and trans alpha methyl piperidine, trans form will be more stable. 2 greater than 1 stability. Okay, I think everyone have noted it down. So let's continue with next example. Okay, so if you are asked to draw this conformer, see this is one of the most and best example to explain the gauge effect, right? If you have to draw gauge, you can place this lone pair here, ethyl here and methyl here. Okay, this nitrogen is having lone pair here, ethyl this side and methyl this side. Now again, if I will say this carbon, backside carbon is having H, Et and Me. Okay, so now with respect to lone pair, one group must be here, one group must be here and one group must be here. So you can observe, if I'll place ethyl here, lone pair ethyl is okay, but ethyl is not okay. If I'll place here, bulky group must be with respect to lone pair, so it is better to place ethyl here. Now again, hydrogen and methyl. So if I place methyl here, methyl, ethyl and methyl repulsion. If I'll place methyl here, so methyl ethyl is common, but methyl with lone pair, that is okay. So hydrogen here. So this is the most stable conformer of this structure. Okay, so I am giving you some generalized format. This carbon connected with any of the groups, having nitrogen connected with any of the groups. In such cases, gauge effect is observed, means in case of NR2, in case of NHR, in case of OR, in case of OH, in case of all these cases, gauge effect is observed. Okay, either it may be due to hydrogen bonding or it may be due to lone pair and bulky group on gauge to each other. Okay, so I think you have understood this entire portion. Okay, so here you can see in all these cases it is 1 2 3 4 1 4 diol, it is 1 2 3 1 3 diol, and now it is 1 2 diol. So let's draw one by one. If I'll say this 1 4 diol, then here first let's recall what are the possible cases. If I'll draw Newman projection of this cyclohexane, and in that, so it's better that draw chair form. So in chair form, if I'll say this chair form 1 2 3 4 means this 1 and this 4, this is OH eclipsed and OH eclipsed. So then you must click in your mind that a better possibility is if rather than repulsive forces, here we have attraction forces. So this carbon is having H this side and the H this side, so it is having attraction forces. So in case of cyclohexane 1 4 diol, you have to remember both conformation is most stable. Why? Because here it is having 1 2 3 4, from this side also 1 2 3 4. 1 4 diol is most stable due to flagpole attraction here rather than repulsion. Okay, now come to 1 3. Now again 1 2 3, then you may think axial case, like so it is 1 2 3 1 3 diaxial attraction here. Okay, so in case of 1 3 diol, you have to remember chair conformer with both OH in axial part. This is up, axial, down, up, it is axial. Now let's take last case. So here if I draw this cyclohexane in 1 2, I think everyone must have drawn this part. Okay, so let's clear it out. Okay, now see, this is your 1. Now this is your, this is the best possibility which we can draw with respect to Newman projection, where I have placed both OH in equatorial. You can see this is number 1 carbon in axial part, and this is number 2 carbon having backside, number 2 having this axial part. So this is your equatorial, this is your equatorial, 1 2, okay, 3, this is your back 4, front 5, and this is 6. So here in 1 2 you can say I have drawn both in equatorial part, and it is having, just like in Newman, it is having gauge, so it is most stable. So simply I wish to draw here with respect to chair, then this OH this side and this OH this side. Okay, keeping both in equatorial, it is having attraction forces, right? Okay, so it's done. I think you must have understood all these 3 cases. Okay, so let's continue further. Understanding strain in different rings. See, we started this topic with Bayer's strain theory, 3 member, 4 member, 5 member, 6 member. And we continued and completed everything about six-membered ring, right? How six-membered ring is stable, how it is Newman projection is drawn, how the chair conformer inverted, and all these things. Now let's come to see remaining part of rings like 3-member, 4-member, and 5-member. How these rings are stable, how these rings exist, and their strain. So first of all, let's study about 3-membered ring. This is your cyclopropane, okay? This interior angle here is 60 degree. All three angles are congruent, all three sides are equal, right? So this V shape this side, so it must be having two hydrogens, right? One, if I am saying this two carbon this side, so one must be back side and one must be this side, okay? Again here also these two are this side, so one must be back side and one must be this side. Here also this and this, so one must be this side and one must be this side, okay? So this is your cyclopropane. Now if we will observe the overlapping, how this bond must have been formed, this carbon one orbital, this bond overlapping must have been done in this format, right? Again this bond via overlapping in this way, and this bond in this part, right? Now if we will see in this case, if overlapping through this part, and again with respect to this bond overlapping occurs in this way, then this orbital is having electron, that's why it is making overlapping. This orbital and this orbital are very close to each other, so there must be very high amount of repulsion and strain, okay? So in reality it never makes overlapping in this way, actually it is slightly bent. So if I will draw, so you can observe the overlapping is nearly in this way, it is slightly bent from this side. Here also in this way, here also in this way, okay? So it is slightly bent then, as you see and imagine. So this is the reason why 3-member rings are considered as having bent bonds. It is not perfect bond, this will be called as bent bonds, okay? So if it is having bent bonds, then you can say that this bond is not perfect overlapping. So if it is not having perfect overlapping, then it is relatively weak, and hence 3-membered rings are having very high strain, as you can see. This is having huge steric strain, angle strain, and huge amount of deviation. So in that case what happens, the ring has having tendency to break down, okay? So generally whenever you come across different reaction mechanisms, whenever you come across 3-membered ring, then remember that there must be some abnormality due to instability of 3-membered ring, okay? So this is about your 3-membered ring. Now if I need to draw the Newman projection of this 3-membered ring, then how will I draw? So let's see. Suppose this is back carbon and this is front carbon, okay? So as per the 3-member ring, now look it at as, suppose this is your front and this is your back. So with this front and back are in front of each other, this front and back. So with respect to this, third one is this side. So third one is this side, okay? So this carbon and this. Now you see, this is having two hydrogens. So this is having two hydrogens, okay? Now this is having two hydrogens, this part and this part. So this part and this part. This back is having one bond this side, okay? One bond with this side and this side. So it must be having two, this and this. Now again this is having H. See, this is 3-membered ring. How? 1, this is second carbon, your 3-member ring, backside carbon, and this is front side carbon. So this is the structure of 3-membered ring cyclopropane in Newman projection. Okay, so note it down perfectly. So I think everyone must have noted it down. Again I am repeating, 3-membered ring, 60 degree cyclopropane. This is not perfectly overlapping. There are bent bonds, so it is unstable. Overlapping is not with respect to the bonds, slightly away from the bond. Now here, if I'll see this carbon, carbon and this side. Now, one more question arises. What about this? How much eclipsing is there? So, if I'll see the eclipsing in this part, it is almost very near to completely perfect eclipsed form. Okay. This part, this hydrogen, hydrogen, this hydrogen, hydrogen are almost perfectly eclipsed. Means if I'll draw this structure perfectly, then this hydrogen is here, this is here. Perfect eclipsing is observed in this. Means the dihedral angle between this CH and this CH is almost 0 degree. Okay, clear? So this was all about your cyclopropane. Now let's come to cyclobutane. Okay, so in cyclobutane, conventional style, if you will see, this angle is 90 degree, this carbon is having sp3, so it would have been 109 degree 28 minute, but it is 90 degree. Now this is just a thought, it might be like this, but if you'll see in reality, then this is not perfectly just like a square, because it is not planar structure. Okay, it is slightly folded. So if I'll draw, approximately it is like this. This angle is approximately 88 degree. Okay, now in 3 dimension, when you will observe this, you will understand it perfectly. It is not perfect square, it is slightly folded structure. Okay, and the bond angle is 88 degree. Now what observation comes from this bond angle? If it was earlier 109 degree 28 minute, means approximately 110. Out of 110, if it is 90, then there is a strain of 20 degree. But now it is 88, means the strain, angle strain is even increased here in this structure. Okay, so first and foremost thing is angle strain is high, right? Now if I'll say about hydrogen atoms, you can see HH. In 3 dimension you won't find this type. Okay, HH. Now this is the structure of cyclobutane. Each carbon is sp3, so it should be almost tetrahedral type. This is folded, V-shaped and V-shaped. Now this interior angle 88 degree, slightly folded. Now here torsional strain as well as van der Waals strain is insufficient amount. Okay, so the structure is not very well stable as compared to cyclohexane. Now if you are said to draw the Newman projection formula of cyclobutane, how will you draw? Across any of the carbon, suppose you say. Okay, so you observe, suppose this is front, this is back. Okay, so here if I'll say this is one carbon and this is another carbon, so it is like this. Okay, this carbon is front 1, this is back 2, this is 3 and 4. Okay, now here this must be having 2 hydrogens. Now if I'll see, this carbon is having, this back carbon is having 1 bond this side, 1 bond this side, so 2 bonds must be with carbon with hydrogen. Now this must be having again hydrogen and hydrogen. Now this is your CH2, CH2. Now here, what about the eclipsing in this part? Eclipsing in this part. So you have to understand, it is not perfectly eclipsed, means the dihedral angle between this CH bond of front carbon and this back carbon CH bond will not be 0 degree, but it is very near to eclipsed. very near to eclipsed. Okay, so this is all about your cyclobutane Newman projection formula. Clear? Okay, so next come to cyclopentane, right? In cyclopentane, in conventional style, if I'll see, then every carbon is having two CH bonds. Okay, this angle was approximately 108 degree, so also it is not having very much angle strain, right? Now let's understand how this structure will be existing in Newman projection formula. So again, it is having front and back, right? So with respect to this 1, 2, 3, this front carbon is having one bond this side, one bond this side, and one bond this side, H, H, and one bond towards back. Now this back carbon is having one this side, and one this side. Okay, now this is your CH2, this is your CH2, now this is your CH2. Now here you can understand it is approximately near to staggered or perfect. This strain here is very less. Okay, these two hydrogens are very far apart, such that the van der Waals strain observed here and the torsional strain due to this CH bond and this CH bond is very less. Okay, so this is the case of cyclopentane. Each carbon atom will be sp3. Correspondingly, the bond angle 109 degree 28 minute is expected. Here you cannot say it is exactly 109 degree 28 minute, but it is very near to that. Okay, so the angle strain is very less. Clear? Okay, so I think we have discussed about 3-member ring, 4-member ring, 5-member ring, and also 6-member ring in detail. So students, let's see some 3-dimensional images and observe whatever we have studied earlier. Okay, so students, now let's see whatever we have studied in conformers in some observational way in the sense in 3-dimensional images. So it's sort of your quiz time. So I'll be asking you first, you just check the image, see it properly, then think what it is and what I am trying to show with respect to that image, then I will explain it, right? So let's see how far you have understood the entire topic of conformations. Okay, so let's start one by one. So first observe this image, what it is all about. So okay, so let's see it properly, what this image is trying to show. If you will see this as carbon number 1, carbon number 2, carbon number 3, and this is again 4, 5 and 6, right? So if you will see properly, it is 3 carbon this side and 3 carbon this side. Isn't it twist boat? Right, here we feel like this is cross, but it is actually, see, this bond is front and this part is your back. Okay, see this 1, 2, it's like that. Okay, so this is your image of this is your twist boat. Okay, so come to next part. Okay, Now let's pick the next one. Now what is this? If we look at this structure properly, you will find that it is short of this. It is what? Chair form, right? Chair form. 1, 2, 3. This side, and this side. Okay. So this is your chair form. You can see here. This is your hydrogen in equatorial, hydrogen in axial. Again, both are having this and this side. See, this one is this side and back side. Every carbon is having 2 hydrogens. Okay. I think it's over. I think this question everyone must have understood, right? Okay, so let's take next example. I think you must be enjoying with this part, right? So you can see here, what is this structure telling? If you'll just imagine the previous structure and this structure, you will find that here it is inverted chair with respect to the last image. See, this is upside. Okay, so this is your inverted chair. You can see this inverted chair. I think everyone must have understood this part. Okay, so next come to this structure. Think over it properly. What is this structure? You can just look at it. It is yes, this is your boat conformation. Okay, this is your boat conformer. Again, you can see, if you remember properly, I have told you trans part, this part V-shaped and this again V-shaped. So this side of hydrogen and this side of hydrogen, these two were making flagpole repulsion, right? And if OH is there, in case of 1,4-diol, it is 1,4 attraction. Okay. So let's take last part. Now first of all, I think you must not be able to observe. Okay friends, so let's observe this image perfectly, what it is telling. So in this image, if you will see, you will find that okay, I think now it is perfectly visible to you, right? So here you can see this is chair conformer. This is 1, 2, 3, 4, 5 and 6. Okay, now this is your 1 position CS3, 3 position hydrogen and 5 position CS3. So it is actually 1, 3, 1, 5 diaxial repulsion. Again, if you will see, this is 2, 4 and 6. All these places are having chlorine. So it is again repulsion. Okay, so it was all about your chair conformer having 1, 3, 1, 5 diaxial repulsion, or 2, 4, 2, 6. You can understand the axial part of downward is having repulsion as well as the axial part of upward is having repulsion. Okay, so I think you have understood all these 5 cases. So let's come to next part. So let's start with some new examples again. First, think about this one. Okay, so what it is all about? So again, if you will observe it properly, you will find that 1, 2, this 3 carbon this side, and 1, 2, 3 this carbon. It is all about your cyclohexane, right? Now let's come to next part. Now what is this? If you will observe this one, you can check it. It is very similar to inverted chair. See, 1, 2. This is having this side, this is having this side, and this is having this side. Inverted chair. Okay. Now let's take this one. What it is trying to say? Think over it. So, this structure is your, again, boat form having flagpole repulsion, right? Okay, so now take this one. Think about this structure. If you will see in 3 dimension, you will find that just color is changed. It is again your boat form only. Okay, clear? Now take this part. Now this part is representing you perfectly about the chair conformer, actually inverted chair. Generally what we do, we draw chair like this, right? This way, this side bent. So here if inverted chair, so it will be this side bent. You can see here, this is bent like this, so it is inverted chair. Okay, so I think you have understood this all parts. So let's take another few examples. Okay, so let's see about these structures one by one. Now what is this telling? This is your, yes, if you can observe it perfectly, you will find that this structure is all about your twist boat. See, this side, it is making cross. Okay, twist boat. One, two, three, four, 5, 6. It is twist boat, right? This part. Let's take next example. So look at this part perfectly. Here, what you will find that in this structure, just observe which one is carbon atom, what it is trying to represent. This is a carbon having 3 bonds this side. Okay, this carbon is connected with this side carbon, and again there are some structures. So it is a 3D image. If we will be able to rotate it, then we can explain it perfectly. So I can just explain you, this carbon is a bigger size atom having simple smaller CH bonds. Okay, C bond is bigger, CH bond is smaller. Okay, let's take another example. Now what is this? This is our chair conformer. Now here I am just trying to explain you the entire part. See, this is your perfect chair. This is your head, this is your tail, these 4 atoms. Okay, what happens if this part is coming in upward side? It will become half chair. Again, if that upward part will come this side, it will become boat. Okay, when boat forms is done, it moves away from each other to minimize repulsion. Then you forms twist boat. Okay, so I think you have understood. Chair, upside, half chair, again up, boat, repulsion mix, twist boat. Okay, so all the 4 cases are done. Let's take this case. Now what it is? If you'll simply see, when you say that 4 atoms are like this and like this, boat form, okay, peak position carbon, and this way 4 atoms in same plane. So in 3 dimension you can see this carbon of front and back are just in front of each other, and this is your boat form. Okay, exact image to show you how this boat form is represented. So let's see our last example of this compound. So this compound is your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is having 10 carbon. It is your bicyclo compound. Its name is decalene. Okay. Now one of the most important question arises, and it is asked if decalene can show geometrical isomerism. Yes, it can show GI. It forms cis as well as transforms. Okay, cis as well as transform. Now look at this image first of all. Then I'll make its conformer. If you will see this image, you will find, see, this is having hydrogen atom in these 2 points. So if both the hydrogens are towards same side, it will be your cis. Again here, either dash or wedge, cis. If one is in wedge and one in dash, then it will be transform. Okay, so with respect to this image, you have understood, right? Now let me draw the chair conformer type structure of this decalene to make you understand how it is represented. See, if I'll see this part, so this is your 1, 2, 3, 4, 5, 6 members, 7, 8, 9, 10. Okay, so this is 10 member ring. This is your decalene, and this decalene is your one part. Another type we can say is now here you can understand this as one part smaller, so it will be bigger and it will be smaller. So this is another decalene. Okay, so this is your decalene cis and transforms, right? So in this way it is represented. Clear? So students, through this lecture we have completed entirely about conformers. From next lecture onwards we will start with optical isomerism. Okay, see you next time.